Imagine a sensor that produces one of 5 readings, from level 0 through level 4. The sender sees the reading. The receiver knows the 5 possibilities and their displayed frequencies, but not the current one. Only a 2-bit label may cross the link. 2 bits can name 4 labels, so at least 2 of the 5 readings must share one reconstructed value. We need a rule for judging an approximation. In this first task, numerical closeness matters. If the true reading is 4 and the receiver reconstructs 3, the error is 1. Squaring that error still costs 1. Reconstructing 0 would cost 16. This declared squared error cost is called distortion. Smaller average distortion means a better representation for this task. Compare 2 simple designs. Design A merges the common reading 0 and 1 at their midpoint, 1/2. The second design keeps those common readings separate and instead merges the rare readings 3 and 4 at their midpoint, 3 and 1/2. Every other reading is reconstructed exactly. Both designs use 4 labels, and both merged pairs are only 1 level apart. Which design has the smaller average squared error? Merge the common pair or merge the rare pair? Choose the common pair design or the rare pair design before we calculate.
I choose the rare pair design. Each merged reading moves by the same half step, but fewer source readings should pay that cost.
Trace one realized case before averaging. Under the rare pair design, source level 4 becomes the reconstruction 3.5. The numerical error is 1/2. Squaring gives a distortion of 1/4 for that occurrence. Level 4 occurs 5% of the time, so this one case contributes 5% times 1/4 to the long-run average. Design A moves levels 0 and 1 by 1/2. Together those common levels occur 70% of the time, so the average distortion is 70% times 1/4, which equals 0.175. The rare pair design moves only levels 3 and 4. They occur 15% of the time, so its average is 15% times 1/4, which equals 0.0375. The rare pair design wins this declared comparison. We have not proved that this is the best possible 4-label compressor. We compared 2 finite designs under one explicit cost rule. That boundary matters because changing the error rule can change the answer completely. 3 finite choices show the trade-off. Exact fixed-length identification of 5 readings needs 3 bits and has 0 distortion. Our 4-label design uses a 2-bit index and has distortion 0.0375. At the other extreme, the receiver can always report the probability-weighted average of the 5 levels. That average, called the source mean, is 1.1. It needs no transmitted index. This 0-bit constant has average squared distortion 1.39. These are only 3 designs. Drawing lines between them would not reveal the best possible compression limit. A fixed index length also differs from the amount of source information that a reconstruction actually preserves. To find the limit, we must allow long blocks and ask the best achievable result over every valid reconstruction rule. Return to the rare pair design. Before the receiver sees a reconstruction, the 5 source readings contain about 2.009 bits of uncertainty. 3 reconstruction labels identify their readings exactly. Only the label 3.5 leaves a choice between source levels 3 and 4. Averaged over every label, about 0.138 bits remain. Subtracting leaves about 1.871 bits preserved by the reconstruction. This average reduction in source uncertainty is called mutual information. Now choose how much average distortion the application will tolerate. Call that the distortion budget. Imagine long blocks from the same memoryless source, meaning that every reading follows the displayed probabilities and does not depend on earlier readings. Consider every compression rule whose average distortion stays at or below the chosen budget. Among those acceptable rules, ask for the smallest achievable number of transmitted bits per reading. Repeat that search for every allowed distortion budget. The resulting best rate is called the Rate-Distortion Function. Its compact notation appears on screen. In the long block limit, it is the least rate compatible with the chosen average error budget. The formula states the same search by minimizing the mutual information over every allowed reconstruction rule. The endpoints make the meaning concrete. With squared error, zero distortion forces an exact reconstruction. The required rate is then the source entropy, about 2.009 bits per reading. If the allowed average distortion reaches 1.39, the receiver may always use the constant 1.1, so zero transmitted rate is available. An average budget does not protect every individual reading from a larger error. Keep the same sensor. Keep the same source probabilities. Now change the receiver's job. The receiver no longer needs an approximate numerical reading. It only needs a category. Levels 0 through 2 are ordinary. Levels 3 and 4 are dangerous. The new distortion is 0 for the correct category and 1 for the wrong category. How many labels are enough for this new task? Do we still need 4 labels, or are 2 labels enough? Choose your answer now.
I choose 2 labels. One label can mean ordinary and one can mean dangerous. The exact numerical level no longer affects the receiver's decision.
2 labels are enough, so one transmitted bit can preserve the entire named task with 0 category distortion. Levels 0, 1, and 2 may share the ordinary label. Levels 3 and 4 may share the dangerous label. This compressor discards more numerical detail than the 4-label design, but that detail has 0 value under the new rule. The phrase "throw away information" is incomplete until the goal is named. Across this playlist, the useful question has always been what the receiver can distinguish. A source model prices possibilities. An observation changes them. Noise blurs them. Codes protect them. A distortion rule declares which distinctions may be surrendered. Information is a relationship among a source, an observer, an allowed operation, and a goal.